So, I've decided to divide this talk into 4 sections, and since I've been allocated 90 minutes, and I really have a 60-minute talk, I decided I would ask for questions at the end of each of the 4 sections, and in that way, we can take advantage of the additional time that's been allocated. So in the first section, I will discuss sort of the prehistory of string theory, which is the period of the 1960s. And then in the second part, I will talk about the first string theories. And the third part will be where the subject got changed from strong nuclear forces to gravity and unification. And then the fourth part will concern something called anomalies and how to get rid of them, their cancellation. So since this is a personal history, I will emphasize works that were done by myself and my collaborators. My main collaborators were André Neveu, Joël Scherk, both of whom I met when I was in Princeton. They came from France. Lars Brink, who was Swedish, and Michael Green, who was British. So a very international group. And so I will pause for questions at the end of each of these 4 sections, as I said. So part 1. So string theory was developed in the search for a theory of the strong nuclear force. So the only force for which there was a satisfactory quantum theory in the 1960s was the electromagnetic force. And the theory that does it is called quantum electrodynamics, abbreviated QED. And this was and still is a well-established quantum field theory of electrons and photons. The goal of the high energy theory group in Berkeley, when I was a graduate student a long time ago, 1962 to 1966, was to construct a quantity called the S matrix that encodes the probability amplitudes for scattering of the particles that experience the strong nuclear force. So such particles are called hadrons. So they are particles such as protons and neutrons that experience the strong nuclear force. The correct theory of hadrons was actually formulated in 1973, and I will come back to that later. It is what's called a Yang-Mills theory, and based on interacting quarks and gluons with a certain symmetry group. It is actually, in retrospect, very fortunate that QCD wasn't discovered a few years earlier, because had it been, it is unlikely that string theory would have been developed, at least for a very long time, since it was the search for a theory of the strong interactions that got us going on this stuff. And had we already known one with a more or less conventional quantum field theory like QED, then we wouldn't have done what we did. So this point hasn't been emphasized previously, but I'm convinced that it's true. So it's just a curious historical fact. So the intellectual leaders of S-matrix theory research in Berkeley, when I was there in the 1960s, were Jeffrey Chu, who was my advisor. He had previously been a student of Enrico Fermi himself, and Stanley Mandelstam. Jeffrey Chu argued that quantum field theory could not explain the strong nuclear force, that power series expansion in the coupling constant called perturbation theory would not be useful for the strong interactions since the expansion parameter is large and such a series expansion would be a very poor way to proceed. This turned out to be wrong for reasons I'll explain later. Instead, Chu proposed that one could deduce the hadronic S matrix, which is the fundamental mathematical object that encodes the strong nuclear force, from some general principles. So what are these principles? The principles of S matrix theory. This matrix, this S matrix, this is an infinite dimensional matrix which encodes all possible scattering processes involving hadrons. And its 2 crucial properties are unitarity and analyticity. This infinite dimensional matrix satisfies S dagger S equal 1, so that's unitarity. And And what that formula means is that the probabilities, which are the elements in the diagonal elements in the S dagger S, are probabilities, and they are positive and add up to 1. So that's unitarity. Just makes that obvious statement. And analyticity means that the singularities of this analytic function are in the right places to ensure that the theory is causal. So certain poles that describe unstable resonances have to be appropriately positioned in the complex energy plane to ensure causality, that cause precedes effect. You have exponential decay of particles, not exponential growth. Another general principle was analyticity in angular momentum, which grew out of work by Tullio Regge earlier in non-relativistic quantum mechanics, but was carried over into this domain. And it's a peculiar thing because angular momentum in quantum mechanics is a discrete thing. I work in units where the Planck's constant divided by 2 pi, which we call h bar, and the speed of light, c, are both set equal to 1. So in these units, angular momentum is just a number, since it has the dimensions of angular momentum, and h bar has the dimensions of angular momentum. And so when angular momentum in these units is an integer, that describes particles called bosons, and when it's an integer plus a half, then it describes fermions, which are the 2 kinds of particles that you have in a relativistic quantum theory. So Regge realized that it's sometimes useful to interpolate between these physical values of angular momentum and consider continuous values. So hadrons, especially the baryons, many of which were discovered in this period in the 1960s. So the baryons are, in the modern interpretation, particles made out of 3 quarks, as the protons and neutrons would be the most familiar examples. And many additional higher mass hadrons were observed to lie in approximately linear and parallel Regge trajectories. So that means the angular momentum J was linear in the mass squared. So S is the mass squared in this formula. And alpha 0 is just the value of this function where it crosses S equals 0. Whenever the function alpha of S is a non-negative integer, J, or a half integer in the case of fermions, there is a stable particle or an unstable resonance of spin J and mass M. So in the case of hadrons, one saw that the whole families of them lie on straight lines given by such a formula, where the Regge slope, alpha prime, is about 1 in units of GeV. GeV is a billion electron volts. Just to give sense to that, the mass of a neutron or proton is approximately 0.9 GeV. So we're dealing with slopes that correspond more or less to the masses of neutrons and protons. So in a scattering reaction where particles 1 and 2 collide and give rise to particles 3 and 4, energy and momentum are conserved. And we write that just in this way, where the index mu goes over the energy and momentum components. So mu takes 4 values, 0, 1, 2, 3, 0 being energy, 1, 2, 3 being momentum. And there are Lorentz invariant quantities given by squares of different combinations, S, T, and U, shown here. And the sum of those 3, these are not independent. Their sum is the sum of the squares of the 4 masses. So one of the crucial ideas that Chu and his collaborators introduced is what they called the bootstrap conjecture. It started out with his collaborator Frautschi, who was about 5 years senior to me, had been his student prior to when I was in Berkeley, and whom I have subsequently overlapped with at Caltech for more than 50 years. So particle exchanges are, according to the bootstrap conjecture, provide the forces that are responsible for their own existence. So if the physical process is given where S is positive and T is negative. And in that regime, you see the particle resonances given by the first series. And they write out all the poles and their residues. And that's the first series here. But this function is supposed to be symmetric in S and T. So it can also equivalently be described as the second series. Now, one has to understand that these series are only convergent in certain regions of the complex plane, and you have to do analytic continuation outside of that region to relate these two expressions. But then you're supposed to have a formula of this type. And the physical interpretation that was associated to this formula is that the exchanges of the forces, which is what the second series is describing, are providing forces between the particles that are responsible for their coming together and having resonances, as described by the first series. So such a formula is only conceivable if you have an infinite spectrum of particles. Otherwise, there wouldn't be any solutions to such an equation. And also, as I said, these series need to be defined outside the regions of convergence by analytic continuation. And this is different from the formulas you would write down in more conventional quantum field theory, where you normally have a finite spectrum and you couldn't possibly have such a formula. So another important ingredient in this discussion is that the resonances are pretty sharp, that the lifetimes are long. So the width of the resonance gamma is proportional to the reciprocal of the lifetime. The exact pole positions in the complex plane are then given by a formula shown here, where S has an imaginary part controlled by the resonance width, and a technical remark that it's on the second sheet of the Riemann surface. That being on the second sheet of the Riemann surface ensures causality, giving rise to an exponential decay rate. If it were on the first sheet, you would have a plus sign in this exponential, which is obviously not what you want. The narrow resonance approximation in this analysis is analogous to the leading or tree approximation in a perturbative treatment of the theory. So those were the general principles that were developed during my years at Berkeley, where I was introduced to this whole subject and way of thinking. And in 1966, I moved to Princeton, where I continued to think about related subjects. And in 1968, Gabriele Veneziano, who an Italian, but he was at CERN at the time, found an explicit realization of the formula that I gave earlier. And it's given in terms of Euler's beta function. So remember, we had these linear Regge trajectories, alpha of S and alpha of T. And he put them in this beta function, which is the ratio of gamma functions, which I'm assuming you're all familiar with. And remember, it interpolates between the factorials. So the beta function is this ratio of gamma functions. And this formula, where the arguments x and y are given by these Regge trajectories as shown, actually satisfies the bootstrap equations. It's really quite an extraordinary thing, because it's an incredibly simple formula, really, and it was much simpler than anyone previously thought could be possible. And the remarkable thing is that Veneziano just pulled this out of thin air. It wasn't derived by some theoretical analysis of a theory. It was just a made-up function. But the whole history of the subject is kind of bizarre. Very soon after Veneziano wrote down his formula, another Italian physicist named Virasoro proposed an alternative to formula, which instead of having two gamma functions in the numerator and one in the denominator, had three in the numerator and three in the denominator. And this also had this same kind of duality, but it had to not just be in the S channel and the T channel, but also in the U channel. Remarkably, these two formulas, guessed without a theory, later turned out to be almost precisely the tree approximation or leading approximation amplitudes given by theories of open strings and closed strings, as I will be discussing. Very soon after they wrote down those formulas, various groups of people, I won't even list all their names because it would fill a whole page, wrote down generalizations of their formulas where you have n particles rather than just 4. Because both of those formulas describe interactions where 2 particles come in and 2 particles come out. So here we could have 2 particles coming in and n minus 2 coming out, for example. Or it could be 3 to 3, etc. So there's more general formula, and I'm only being schematic here. I don't expect you to absorb all the details. That would be unrealistic. That involves a certain measure, which I'm not even going to give you the formula for. But it contains step functions that ensure that these y's satisfy these kind of inequalities. And it also contains some delta functions that ensure that there are actually only n minus 3 integrations rather than n. So I'm only trying to give you an impressionistic view, and a precise description would take more time than I want to take. So the particles in the previous formula are required to belong to the adjoint representation of a group, a so-called gauge group, such as an orthogonal group or a symplectic group. And the complete tree or leading approximation for the amplitude then takes the form where you take the amplitudes A sub n given by the previous formula, and then with the group theory coefficients C sub n, which are given by traces of products of matrices, which tell you which particle in the representation of these gauge groups you have, and then you sum over all the permutations. And that, in this way, you build the group theory into the formula, and this Tn is then actually the total amplitude, including the group theory factors. So that was a formula for n open string particles. And there was another formula for n closed string particles, which generalized Virasoro's formula. So the first formula generalized Veneziano's beta function formula, and this formula generalizes Virasoro's formula, the one with 3 gamma functions in the numerator and 3 in the denominator. So that would be the special case n equals 4. So this integral can be done when n is 4, and it gives those ratio to the gamma functions I showed earlier. And then again, there's some other measure. In this case, the variables are integrated over the entire complex plane without any ordering. But there are delta functions in this measure that ensure that that positions of 3 of them can be fixed at particular values and wouldn't just integrate over the other n minus 3. You can make a change of variables so that instead of integrating over the complex plane, you're integrating over points on a 2-dimensional sphere. So you can projectively relate the complex plane to a sphere. In 1969, Fubini and Veneziano showed that these formulas have consistent factorizations on a well-defined spectrum of single particle states. In other words, if you take the residue of a pole in a certain channel, that residue corresponds to a product of amplitudes with fewer particles in them. And this works for all the different poles and all the different channels. So it's an extraordinary consistency of this set of formulas, which prior to this looked kind of arbitrary and manufactured. And in fact, they showed that the spectrum of particles can be described by an infinite number of harmonic oscillator type variables. Remember, in quantum theory, a quantum oscillator is something with this commutation rule. And so you have an infinite number of them, except that the one becomes a minus sign for the time component. Whoops. but otherwise they're like ordinary oscillators. So there's one set of such oscillators in the Veneziano case and two sets in the Shapiro-Virasoro case. And the existence of these formulas with a consistent factorization like this meant that these were not just an arbitrary bunch of made-up functions, but actually the amplitudes from a consistent underlying theory. And so this raised the question, what is that theory? So that's the end of the first part of my talk. So let me pause at this point to ask if there are any questions.
I have a question regarding sort of the S matrix program from the beginning, where how much progress would you say that there was made in trying to, not before, the Veneziano amplitude, but before that, with Chu and Fatucci, Low, and all these people working in this sort of S matrix, approach, how much progress was made? There's a book I was looking at called The Analytic S Matrix by Chu. And there's some very impenetrable formulas, the strip approximation and so on and so forth. And again, I found it very difficult to go through, but I was always curious, how much progress did that sort of make before, you had the, dual resonance models, the Veneziano amplitude, and of course, QCD and, and those developments kind of washed away this sort of, Ray J trajectories and bootstraps.
Yeah, well, in the 8 years from 1960 to 68 before Veneziano's formula, there was all sorts of interesting ideas were being developed and influenced the subsequent work, and partly for lack of time and because they're perhaps not as interesting as some of the other things, I've omitted describing them. There were things called finite energy sum rules by Dolan, Schmidt, and Dolan, Horn, and Schmidt, which were very influential. And there are quite a few other things that I'm probably not even thinking of at the moment. So there was plenty to keep me busy and entertained during my years in Berkeley. The work that I did as a graduate student was not important in the subsequent history, but certainly helped me to learn about the concepts that would be important to me later. Well, there was a lot. There were quite a few clever people doing interesting things, but and I've mentioned one of them. Any other questions? No. Okay, so I will proceed. Part 2, the first string theories. So the fact that there was a consistent factorization of the poles in these formulas given by these fancy integrals on a well-defined spectrum of particles was the first indication that these are actually theories and not just intriguing made-up formulas. So that raised the question, what are these theories? And in 1970, an independent work by 3 people, they did not collaborate, so the 3 independent works, independently interpreted the spectrum and the amplitudes as arising from the theory of a one-dimensional extended object, which came to be called a string. I don't remember whether any of these people used the word string, and that's really beside the point. The important fact is that they had the right concept. It is a one-dimensional extended object, and this understanding was of course extremely influential. And the reason that the integrals have the number of integrations that they do can be understood in terms of the string picture. So the Veneziano amplitudes, remember those were the first step which involved real integrals, were described interactions of what we call open strings. So an open string is just a one-dimensional curve with 2 ends, just a finite piece of string of infinitesimal thickness. So those are what we call open strings, and it was the interactions of these open strings which can break in 2 or rejoin that are described by the Veneziano or extended formula. And for the Shapiro-Virasoro case, we were dealing with closed strings, which are just loops with no ends. And these can touch at a point and rejoin to make two such loops can touch at a point and rejoin to make a single string. And those are the interactions that take place in the Shapiro-Virasoro case. So this physical picture of what these abstract formulas meant was very influential, of course. So remarkably, the formula, as I pointed out, the formulas preceded the interpretation. Everything in this field is done backwards. I don't know why, but that's how it is. The string tension is related to that. Remember that parameter that gave the slope of the Regge trajectories, which we called alpha prime? So that's a characteristic of the string, and the tension of the string is just given by the reciprocal of this Regge slope. Remember, everything is in units where h bar on c is equal to 1, so such a formula is dimensionally correct with that understanding. And the way to think about it is that strings sweep out two-dimensional surfaces called world sheets in space-time. And the various formulas that one is dealing with are associated with these two-dimensional surfaces. So in the case of open strings, the amplitudes can be expressed as integrals of n particles attached to the boundary of a world sheet that is topologically a disk. That would describe the leading order in a perturbation expansion. And the higher order corrections to that would add handles and other complications to this disk. So each different ordering of the n particles on the boundary of this world sheet carries a different group theoretic coefficient that I alluded to earlier. The closed string amplitudes given by the Shapiro-Virasoro formula remember, it had a two-dimensional integral for each particle. And so the interpretation is that in this case, you're dealing with a world sheet that is topologically a two-dimensional sphere, and the n particles are just points on the surface of that sphere. And in this case, there's obviously no ordering between the particles, and you can use symmetries to fix the positions of 3 of them, and then the rest of them are integrated over the entire surface in the formula. So having found the spectrum and the tree approximation amplitudes, it now became possible to study what are called radiative corrections, or loop amplitudes. In quantum field theory, when given, such as quantum electrodynamics, for example, you do expansions in the coupling constant, and these are given by Feynman diagrams, and the leading term is what's called tree diagrams, and the higher order radiative corrections involve diagrams in which there are particles that go in loops, and so they're called loop amplitudes. And so that terminology is carried over, and so what one wanted to know is the formulas for the radiative corrections to these formulas. Since we now claim we actually have a theory, it should be possible to discuss the higher order terms in the perturbation expansion. And these are given by integrals associated to higher genus Riemann surfaces. So my personal history is I graduated from Berkeley and then became junior faculty in Princeton for 6 years. And I followed these developments with interest, but as you see, I didn't mention myself yet in the subject. I wrote a few insignificant papers that I will skip, but my first paper that I think is worthy of bringing attention to was a 1970 paper that I co-authored with David Gross, André Neveu, and Joël Scherk in Princeton. So in our paper, the GNSS paper, we studied open string one-loop amplitudes. So the relevant world sheet in this case is topologically a cylinder with 2 circular boundaries. So just a finite length cylinder. So it has two circular boundaries. And there were two cases that we needed to consider. And in the first case, all four of the particles participating in the reaction are attached to one of the boundaries. And in the second case, two of them are attached to each of the boundaries. So two on the first boundary, two on the second boundary. Particles 1 and 2 on one boundary, particles 3 and 4 on the other boundary. We had two different calculations we needed to do. And obviously the integrals are going to be more complicated than the ones I showed you. So I'll be even more schematic in my presentation. So in the first case, the integral has a divergence, which had been previously noted by Neveu and Scherk. And they also developed a procedure for sensibly removing that divergence. So I don't want to describe that. Let me just say that that case was okay. And the case that was really more important was the second case, where there are two particles on each boundary. And what we discovered is that this amplitude contained unexpected singularities, branch points, in the complex coordinate S, in the S coordinate. Remember, we had particle 1 and 2 on one boundary, 3 and 4 on the other boundary. So if you think of that as particle 1 and 2 going in and particle 3 and 4 coming out, then if you cut the surface in the middle, you see a circle. So that's just slicing the cylinder. In the middle, you see a circle. And it was in that variable that one was finding these branch points. And if we have a consistent theory, there shouldn't be such branch points. These were violating unitarity. So unless one could, these were not particle thresholds singularities, they were something else. So unless one could eliminate these branch points, there would not be a consistent theory. And everything that I've told you up to now would go down the drain, and it would be the end of the subject. But since I have more to say, it means we found a solution, or a solution was found. Actually, we weren't the ones who found the solution. Rather, we published our paper with these unacceptable branch points, and then the following year, a fellow named Claude Lovelace, who was at CERN in Geneva, Switzerland at the time, rescued the theory by observing that these singularities would become poles, which would have a sensible interpretation rather than branch points, provided that the Regge intercept, remember the formula for the Regge trajectory had an alpha 0 in it, if provided that's 1, and the dimension of space-time was 26. This seemed to us at first to be completely bonkers, because why in the world should there be 26 dimensions? We knew perfectly well that there are 4 dimensions, 1 time and 3 space, and none of us had ever questioned that. Nobody in Berkeley or Princeton or anywhere else was saying that there could be a different number of dimensions. It is true that there were a couple of relativists called Kaluza and Klein around 1914 or 15, just after Einstein's famous general relativity work, suggested that there could be a 5th dimension and that electromagnetism would have something to do with that. But that never got any traction, and isn't the modern viewpoint either. But that was the only prior mention of the concept of having extra dimensions of space, and that was just in the context of general relativity. We were not doing general relativity. We wanted to understand the strong nuclear force. So none of us had questioned 4 dimensions before this, but Lovelace's discovery forced us to either drop the entire subject or else take the extra dimensions of space, of which there are now 222, seriously. So why should hadrons require extra dimensions? This didn't make sense to us. Why should the spectrum contain a massless spin 1 particle? That's what this alpha 0 = 1 means. This was very surprising. These are certainly not properties of hadrons, and were totally unexpected. So Lovelace's poles have a nice physical interpretation, because they describe poles in the reaction 1 + 2 goes to 3 + 4 And as I mentioned, when you slice that cylinder, you see a circle. And a quantum state of the circle is a closed string. So here we have a process in which two open strings scatter, create a closed string, which then decays back into two open string states. So this is a discovery of what's called open string, closed string duality. And it's an important principle even in modern aspects of string theory. So this is, but that required that this intermediate state be a pole, not a branch point. And that required alpha 0 equal 1 to equal 26. Now, it turns out, for these particular choices, this theory has a much larger symmetry than it has for any other choices. And it's given by an infinite dimensional algebra called the Virasoro algebra. These indices M and N go from minus infinity to plus infinity over the integers. And and without this anomaly term, if you ignore the last term, these generate the group of conformal symmetries of the two-dimensional string worldsheet theory. So in 2 dimensions, the conformal group is infinite dimensional, and these are the generators of that symmetry. So it's an important requirement that the physical spectrum described by all the oscillators subject to the Virasoro constraints not contain any negative norm states called ghosts. Remember when we had oscillators, alpha and mu, I wrote down for oscillators earlier, they had time components. And those time components generate a Fock space with states of negative norm. And so what these Virasoro constraints do for you is they eliminate the negative norm states from the spectrum, only leaving positive norm states. And this is crucial because if you had these negative norm states, it would be a violation of unitarity, and it would mean, again, that the theory was nonsensical. So this was further evidence that Lovelace's proposal was essential for getting a physically sensible theory, even though 26 dimensions seem completely bonkers to us. And it was a challenging mathematical problem to prove that the spectrum only has positive norm states when the Virasoro constraints are taken into account. And that proof was carried out by 2 different methods, by Brouwer on the one hand and by Goddard and Thorne on the other in 1972. So a consequence of the conformal symmetry of the worldsheet theory is that only physical excitations of the string are in the 24 dimensions that are transverse to the string. So we're in 26 dimensions. If you think of a line embedded in 25 dimensional space, there's one dimension that's orthogonal to it, and it's 24 that are orthogonal to it, and the one that's parallel to it. So the excitations are all transverse. Now, in 1971, some interesting things happened, and a second string theory was discovered. So Pierre Ramond, who was then at Yale, introduced a string theory analog of the Dirac equation, which is the relativistic wave equation for a free electron. And his proposal was that just as the string's momentum is there is zero mode of a density along the string, so sigma parametrizes the string, the Dirac matrices should be the zero modes in the same way of densities on the string, gamma mu of sigma. And so he introduced an object, gamma mu of sigma, with certain anti-commutation formulas, and generalizing Dirac's formulas, and then formed the analog of gamma dot p, which is what you have in Dirac theory, and studied its various Fourier components to define operators F sub n. And so that gave Ramond a stringy generalization of the Dirac equation. So this is the string theory version of the Dirac equation. So it's an infinite dimensional equation. So it describes not just a massless spinner, but an infinite spectrum of particles lying on linear parallel register. So later, I was able to show that M has to be zero in this theory. Ramond also observed that the Virasoro algebra generalizes to what's called a super Virasoro algebra with odd elements in addition to the even elements that we discussed earlier. So these odd elements have anti-commutation relations. In other words, this is an anti-commutator, and they give rise to the Virasoro generators L in this manner. So this was one of the first examples of what's called a superalgebra, where you combine commutation relations with anti-commutation relations for an extended algebra. And soon thereafter, the mathematician Victor Kautz gave a complete classification of simple superalgebras, extending Cartan's classification of ordinary Lie algebras. In March of 1971, André Neveu and I introduced a second bosonic string theory, and it has a similar structure to Ramon's theory, but the periodic density, which was gamma mu sigma for Ramon, is replaced by an anti-periodic one. So when you go around the string, it comes back with a minus sign. And then we could form the Fourier modes of that, analogous to what Ramon did, except that the index R now has to be half integer rather than integer to be compatible with this anti-periodicity. And these are the odd elements of a similar superalgebra. I should say this work was done before we were aware of Ramon's work, but his work was prior to ours. So together with Charles Thorne, we showed next that the bosons that are given by the theory that Ramon and I formulated, together with Pierre Ramon's fermions, combine into a unified theory of bosons and fermions. Ramon had only discussed free fermions. He didn't talk about interactions. So our bosonic theory was interacting, and then in this work we were able to make fermions interact and bosons interact with fermions, etc. And this was actually an early version of superstring theory, although there were important issues we didn't yet understand. And I was able to emulate Brouwer's proof of the no-ghost theorem for the Veneziano string, and to show that that this theory again has a peculiar critical dimension, but instead of being 26 dimensions, it turned out to be 10 dimensions. So my attitude at the time was that this was a big step in the right direction, and our next theory, if we're lucky, will be 4 dimensions. But that's not the way the history worked out. So I'm running near the end of my time, aren't I? Let's see. I started at 10:30. Okay, I still have plenty of time. So the critical dimension is 10. Later in 1971, Gervais and Sekita wrote down a 2-dimensional action. So it looks like a free boson from 10 bosons and 10 fermions, because the index mu runs over space and time, which takes 10 values. And they noted that this theory has supersymmetry. Okay, transformations where X transforms into psi and psi transforms into X. These are fermionic symmetries, which were called supersymmetries. And this was the first example in the literature of a field theory. This is a trivial free field theory in 2 dimensions. Trivial as you can imagine, but nonetheless, it was the first example of a theory with supersymmetry. And the existence of the possibility of such a symmetry was kind of shocking to people, because there previously had been a theorem due to Coleman and Mandela, which basically said that there could not be symmetries relating different spins. And here was an explicit counterexample to that previous theorem. Obviously, they had introduced a subtle assumption, which wasn't glaringly false, but turned out to be false, in proving their theorem. So this result of Gervais and Sekita motivated, I went in the wrong direction. Motivated Wes and Zumino construct four-dimensional interacting theories with supersymmetry. And they did this in 1973-74. And their work inspired the construction of supersymmetric extensions of the standard model of elementary particles and subsequent experimental searches for supersymmetry partners. So even though string theory wasn't terribly popular in these days, there were a few hundred people working on it, this attracted the interest of a wide segment of the particle physics community. There were various reasons to believe that there was a good chance that supersymmetry particles would be discovered at the Large Hadron Collider, which started operating early in this century, but so far they have not shown up. In 1972, I left Princeton and moved to Caltech. Murray Gell-Mann offered me a position called a senior research position. And this was really very fortunate for me because the job market had just collapsed at that time. There had been exponential growth in the preceding years, and exponentials like that always have dramatic conclusions. And this was just when that happened. So for my first 12 years at Caltech, my position was called research associate, which doesn't sound very fancy, and many people felt sorry for me. But I didn't feel sorry for me. The same position is currently called research professor, which sounds much better. And in fact, I had complete freedom to do what I wanted and funds to invite all of my collaborators to come and work with me. So I have no complaints about all this. I've remained at Caltech ever since, and I inherited Feynman's office in 1989 and retired in 2015. So the story has various twists and turns. So a quantum field theory called QCD, or quantum chromodynamics, which is somewhat analogous to QED, a little fancier because it's based on the non-abelian group rather than QED, which is based on the abelian group U1. And anyway, this theory was formulated in 1973. And various people contributed to this. Gell-Mann introduced quarks and gluons, as well as the group SU3. Gross and Wilczek, as well as Politzer, established a crucial feature called asymptotic freedom, which earned them Nobel Prizes. What the asymptotic freedom does for you is it means that even though you're dealing with strong interactions, at high energies, the interactions become weaker. And so that's what the asymptotic freedom stands for, is that the interaction strengths get weaker asymptotically. And therefore, perturbation theory is useful, after all. You remember Chu had argued against field theory for the strong interactions because the interactions are too strong for perturbation theory to be useful. So this is how that complaint was circumvented. The success of QCD eliminated the need to formulate a theory of hadrons based on strings. Also, string theory at that time had problems. Another exciting development in 73-74 was the completion and acceptance of the standard model. So the standard model combines QCD with the theory of the weakened electromagnetic forces, which are described by Yang-Mills gauge group SU2 times U1. It also predicts the existence of a new particle that hadn't been discovered in this era called the Higgs boson. It took a long time to be discovered, but it was found by the ATLAS and CMS collaborations at the LHC and CERN in 2012. So after 50 years, the standard model still survives essentially in its original form. So it's a great triumph of theoretical physics and has nothing to do with string theory. Or does it? So these developments completely pulled the rug out from under string theory, which rapidly fell out of favor. A community of several hundred rapidly declined to a few diehard stragglers, including myself. It's an open question whether there exists another string theory, not yet discovered, that is equivalent to QCD. Such a dual description of QCD would be useful, but we don't know any such theory so far. So this is the end of the second part of my talk, and I will call for any further questions.
So something. Oh, go ahead.
Oh, so I'm not extremely familiar with history of string theory, so I'm coming into it from like interest in representations. But since Virasoro algebra describes like conformal transformations in two-dimensional conformal field theory, and operator product expansion was like already developed, was CFT like considered at the time, or it seems to have only begun becoming like popular in 1980s? Uh, why is that?
Yeah, so when you formulate string theory in terms of the string world sheets, the world sheet theory is the conformal field theory. With this infinite dimensional Virasoro algebra, and we didn't know all the tools of the trade for conformal field theory back in those days, and it was later on that there was influential work in Russia by Belavin, Polyakov, and Zamolodchikov on various general aspects of two-dimensional conformal field theory, which is very influential work. We didn't have all the tools, but we were certainly dealing with the right kinds of objects.
Thank you.
I was wondering about the impact of Toff's large N paper, where you were essentially at the end you were saying about a sort of dual description of QCD, and in that paper, which was written in 1974, he links quantum field theory, the SUN and the large N limit, Yang-Mills theory to he talks about like these functional integrals coming from like Chu, Mandelstam, and all these like dual resonance models and such. But and this kind of idea is later developed in the ADS/CFT correspondence. But I'm very curious, like the idea that string theory and like quantum field theory were the same or similar or had relations. Like that idea itself, it didn't come from ADS/CFT, but dates all the way back to 1974. Right. And so I was wondering about the relationship, and was that popular? Was that something you guys were thinking about?
Yeah, this is an interesting story. Ed Hooft was a complicated guy. In the decade of the 1970s, he wrote about 10 papers which are masterpieces in quantum field theory. One of the great scientists of his generation. And one of them is the paper you're referring to, where he pointed out that at large N, certain gauge theories which have a parameter N, like say SUN gauge theory, at large N, that the Feynman diagrams, which get very meshy, can look like they're approximating a string world sheet. He did that on the one hand. On the other hand, he was one of the fiercest critics of string theory, extra dimensions, and supersymmetry. So he's a brilliant guy, and I admire him greatly, but he was dead wrong on those opinions.
Yeah, I find that very interesting because you can read his papers from like his nuclear physics B paper from the 1980s. And he has like very brilliant ideas to me. And he's talking about like black hole microstates essentially, and this idea that if you take like a black hole and like these microstates are sort of like in relation to elementary particles, and then he links them to string theory and S matrix theory. But he seems very reluctant, to me at least, in that paper to like explicitly mention string theory. But then like Susskind obviously is happy to explicitly mention string theory in the 1990s.
Yes. Yeah, I agree with you. I have nothing to add though. Any other questions or comments? Not hearing any, I will move on. Gravity and unification. So in 1973, Yoneya in Japan interpreted the massless spin-2 state in the closed string spectrum of the two theories I've described as a graviton. The graviton is the quantum particle for gravity, just as the photon which is spin 1, is the quantum particle for light. With this identification and a theorem due to Weinberg a number of years earlier, it was easy to show that string theory agrees with general relativity at low energies compared to the string scale. Similarly, the massless spin 1 states in the open string spectrum could be interpreted as gauge theory particles, and this had been shown in 1971 by Neveu and Scherk. In 1974, Scherk and I proposed to interpret the string theory as a quantum theory of gravity, unified with gauge theory forces, a potential theory of everything, rather than as a theory of hadrons, which was our motivation up to that point. Now, this reinterpretation requires that the string length scale is roughly the Planck scale, 10 to the minus 33 centimeters, rather than the nuclear scale, 10 to the minus 13 centimeters, 20 orders of magnitude smaller. So this is comparable to the ratio between the size of an atom and the radius of the Earth's orbit. So this was a rather dramatic change in viewpoint in the development of string theory. Scherk and I were unaware of Uneia's prior work. We were actually proposing much more than he did. He emphasized that you can recover GR in a certain limit, whereas we were proposing a unified theory of all forces. At this time, I knew what I would be doing for the rest of my career. I was absolutely convinced of that, and that's, in fact, how it played out. So this proposal has several advantages. First of all, the existence of gravity is predicted by the theory. We did not set out to construct a theory of gravity. We just built something for another purpose, and there it was. Secondly, we already knew from our prior work that string theory does not have what are called ultraviolet divergences. In other words, the integrals associated with loop amplitudes do not have bad divergences at them. The stringiness somehow softens that high energy behavior. And if you just take Einstein's general theory of relativity and try to interpret it as a quantum theory, it has very severe ultraviolet divergences. The standard model has ultraviolet divergences too, but they're of a kind called renormalizable. And when you have renormalizable ultraviolet divergences, there's a systematic technique for handling them, effectively removing them, and getting sensible finite results. But those techniques are not applicable to general relativity. So finding a quantum theory of gravity free from ultraviolet divergences we thought was pretty exciting. In a gravitational theory, extra dimensions could be a good thing. As I said, had no idea about extra dimensions when we got into this business. But here, once we realized we were dealing with gravity, we also realized that in this context, which was the context that Klutz and Klein had been thinking about in 1915 or whatever, and in this context, that makes sense. And so the idea, of course, is that the extra dimensions, 6 of them in the case of the superstring, would be compact solutions of the equations. So in other words, you can't just take the 6 extra dimensions and assign an arbitrary geometry to them, but you can assign geometries that are compatible with the equations of the theory, and there's an enormous range of possibilities for doing that. The simplest thing to consider is a 6-dimensional torus. For that, the mathematics is relatively straightforward. For more complicated geometries, the math gets much harder, of course. And the torus is not realistic. And the reason it's not realistic is it doesn't break any of the supersymmetry. And that's one of the things you need to do to make contact with reality. And another appealing aspect of this proposal is that that this kind of theory unifies gravity with the gauge theory forces, which are being described by the same theory. So this was a serendipitous theoretical discovery, something that's very unusual. Theoretical discoveries generally concern the subject that the investigator set out to explore. The best known serendipitous scientific discoveries are all experimental or observational. Dynamite, insulin, X-rays, radioactivity, penicillin, the Big Bang cosmic microwave background. So these are famous examples of serendipitous discoveries, but none of them are theoretical. This is very unusual. I'm not saying it's good or bad, it's just unusual. So how was our proposal received? Joël and I spoke about our ideas at various conferences and seminars, and most people were polite and showed interest. A few important scientists, such as Gelman and Zumina, stated that our proposal was potentially very important. Yet our work was largely ignored. So why? I believe the answer lies in the sociology of the profession at that time. Not that anybody had it in for us. Relativists who thought about black holes, the geometry of the universe, etc., had no use for quantum theory. It was far removed from anything of interest to them. Particle theorists who were interested in understanding phenomena that could be observed in current or future accelerators had no interest in gravity. There was a lot of interest in supersymmetry, but not in gravity. It was far removed from anything of interest to them. If you wanted to build an accelerator that would probe gravity, you would have to have energies 15 or 16 orders of magnitude larger than the energies of the LHC. And such a machine would have a ring comparable to the radius of the Earth's orbit, which I don't think we're ready to construct yet. Now, both groups of scientists were correct in their opinions, of course. Therefore, the communities were completely disjoint. A proposal that would bridge the gap had no takers. And it took a decade for this to change. But when it did, it happened very suddenly. So there were various developments along the way that were influential in the subject. One of them was the discovery of what's called supergravity. So supergravity is a supersymmetric extension of general relativity. It's a quantum, I call it a quantum field theory, but just like general relativity, it's not really quantum, it's classical. It was formulated for four-dimensional space-time in 1976 by Friedman, van Nieuwenhuizen, and Ferrara, and their breakthrough paper was followed soon thereafter by one by Deser and Zumina, which introduced a clever way to simplify some of the calculations. So this supergravity work was very important, and I knew that I needed to understand it. And it was important in the development of string theory. One-dimensional space-time supersymmetry. So in 1976, Joël Scherk and Olive proposed a projection of the RNS string spectrum. So the theory as formulated by Neveu Neveu had had some pathologies. Even though the 10 dimensions got rid of the negative norm states, it still had a tachyon, which is negative mass squared, which is crazy, and some other less than optimal properties. So Joël Scherk and I proposed a projection of our theory, restricting it to a theory that has roughly half as many states. And this was a consistent projection that removed roughly half the states from the theory, including the tachyons. So after the GSO projection, the theory no longer has a tachyon. And they showed that after you impose this projection, the number of bosons and fermions is equal at each of the mass levels. So there are an infinite number of mass levels in the string spectrum, and the number of bosons and fermions matches at every one of those levels after this projection. So this was compelling evidence that this theory has 10-dimensional space-time supersymmetry after this projection. But it was not a proof. It just showed the other equal number of bosons and fermions. Proving that it has a symmetry requires studying the interactions as well. The supersymmetry is necessary for the consistency, actually, because the spectrum contains a massless particle called the gravitino, which is the gauge particle for the supersymmetry. So in 1976, the 10-dimensional supersymmetry proposed that these people proposed was distinct from the 1971 worldsheet supersymmetry identified by Gervais and Sakita. So the supersymmetry of the string worldsheet and the supersymmetry of the 10-dimensional space-time theory are separate things, even though they both involve fermionic symmetries. And they were separated in time by 5 years. So the GSO projection is actually required for consistency, and the theory that we had developed was inconsistent until one imposes this projection. Then the theory has supersymmetry in 10-dimensional Minkowski spacetime. I should also remark that the 26-dimensional bosonic theory also has a tachyon, which is lethal, and that theory does not admit any projection that gets rid of the tachyon, so that theory cannot be fixed by an analog of the GSO mechanism. So once you perform the GSO projection and take that as your theory, then you have supersymmetry in the 10-dimensional Minkowski spacetime. But this symmetry, of course, if we want to connect to the real world, has to be broken. And it can be broken when the extra dimensions are compactified. And exactly how that works is a long and complicated story. But it is what we expect will happen. So there are an enormous number of possibilities for actually carrying out this compactification. And back in this era, the only thing we were technically able to do is to study the torus, which doesn't break any supersymmetry. In 1976, Brink, Scherk, and I constructed a quantum field theory, which is supersymmetric Yang-Mills theory. We first constructed it in 10 dimensions, where it's a non-renormalizable theory, but it's important, though, because it captures the massless sector of the superstring. And by a method called dimensional reduction, we also constructed the Lagrangian for what's called n=4 super Yang-Mills theory in 4-dimensional space-time. So supersymmetry charge in 4 dimensions has 4 components, and there are 4 such symmetries, so that's 16 supersymmetries. But actually, this theory also turns out to have conformal symmetry in the 4-dimensional sense, and there are also conformal supersymmetries. So this theory has a very rich symmetry and is a very interesting theory. It's well defined for any Yang-Mills gauge group, although unitary groups are the ones most studied. And this theory has played an important research since 1997, for reasons I will allude to later. A couple of years later, Kremer, Julia, and Scherk in 1978 constructed another field theory, namely 11-dimensional supergravity. So it's a theory somewhat in the same spirit as the Friedman et al. Theory, but in 11 dimensions. 11, it turns out, is the highest dimension in which it's possible to have a supersymmetric theory. The number of fermions increases exponentially as you increase the dimension, and once it gets beyond 32, there are no theories. And so 11, so the basic spinor in 11 dimensions has 32 components. So anyway, this theory contains 3 fields. In addition to the graviton, it has a gravitino, and it also contains a 3-form tensor, so a 3rd-rank antisymmetric tensor field. In the early 1980s, there was quite a bit of research studying ways to compactify the 7 extra dimensions in an attempt to get something realistic out of this 11-dimensional supergravity. This was not successful. What was done because it drew people into the community of thinking about connecting gravity to the standard model. So I had mentioned that there was no interest in doing that previously, and this helped to raise people's awareness of the potential for looking for a quantum theory of gravity. So this is a very beautiful theory, but it has ultraviolet divergences. A good question was whether it could be a low-energy approximation to a consistent, well-defined quantum theory. And this question was answered in the affirmative much later, in 1996. And this quantum theory has been given the name M-theory. At that time, it was also discovered that it has profound connections to superstring theory. So 11-dimensional supergravity, which seemed like an oddball disconnected from string theory, actually, once you understand M-theory, is related. Part of the story. So let's say a bit more about Joël Scherk. In 1978, I spent the academic year 1978-79 at the École Normale in Paris, supported by Guggenheim. And while there, I collaborated with Joël Scherk. We devised novel ways to break supersymmetry and generate mass when extra dimensions are compactified. And it's not clear to me whether any of these tricks will be ultimately useful, but anyway, they are available in case they turn out to be useful. Joël Scherk tragically died in 1980 at the age of 33. Had he lived, he undoubtedly would have been a major contributor to subsequent developments. So let me now return to superstrings. In 1979, Michael Green and I began a collaboration with the initial goal of understanding the 10-dimensional space-time of the GSO projected RNS string theory. And whenever possible, we also collaborated with Lars Brink. Our work was mostly carried out at Caltech, but also at Queen Mary College London, which is where Mike was based, and at the Aspen Center for Physics in the Colorado Rocky Mountains, where I have spent more than 50 summers. Green and I formulated and named the Type 1, Type 2A, and Type 2B superstring theories. We proved the 10-dimensional space-time supersymmetry of the spectrum and interactions in each case. We computed various tree and one-loop amplitudes and elucidated their properties. We formulated superstring field theory in the light cone gauge for the Type 1 and Type 2B theories. And we formulated an alternative superstring worldsheet theory with manifest 10-dimensional spacetime supersymmetry. The previous formulation emphasized the 2-dimensional conformal symmetry. So this alternate formulation emphasized the spacetime symmetry. To say a word about Type 2B supergravity. So Type 2B supergravity is the gravitational sector of the Type 2B superstring. In 1983, I wrote a paper about the equations of motion of this theory in the supergravity approximation. In a footnote, I pointed out that the equations of motion have a solution describing a 10-dimensional geometry of the form 5-dimensional anti-de Sitter space times a 5-dimensional sphere. This is analogous to the ADS4 times S7 solution of 11-dimensional supergravity that had been discovered 3 years earlier by Freund and Rubin. The geometries ADS4 times S7 and ADS5 times S5 feature in the famous 1997 holographic duality paper, or ADS-CFT paper of Malvicino. His paper has approximately 20,000 citations. The primary example is a duality, i.e. equivalence, between the ADS5 times S5 solution of the Type 2B superstring and n equal 4 four-dimensional super-Yang-Mills theory, both of which have PSU 22/4 symmetry. That's a supergroup. In the past 25 plus years, this duality has been studied extensively, as the citation number indicates. I kind of kick myself for not noticing that these two different things, which I had helped to formulate, both have the same symmetry. But anyway, I have no regrets. So that's the end of part 3 out of 4. So I will ask whether there are any further questions at this time.
Can you comment on quantization some more? You mentioned, there's like different quantization approaches, like and covariate and so on and so forth. And, this idea that where you'd basically like switch backgrounds, right? If you had like an easy covariant method. And I was kind of thinking like, how much were you guys thinking about, being able to do that and being able to, switch geometries or backgrounds and so on and so forth? Because, it's formulated in terms of like the space-time is Minkowski, right? So, but then you can go to curved geometry and different kind of constructions, and how much of that was developed at this point?
Yeah. So most of the work that I did with Michael used what we call a light cone gauge, where one uses the gauge invariance to set certain null directions of vectors equal to 0. This was adequate for what we were trying to do. Some of the more covariant approaches using standard techniques in quantum field theory for covariant treatments of gauge symmetries are applicable in string theory, and they are in some sense more elegant and turned out actually to be useful for certain purposes. So that's perhaps the more fundamental approach. So we did most of our calculations using light cone gauge. I just discovered that it's noon, or 5 minutes to 2, and I'm supposed to end at 12, and I'm only presented 3 of the 4 parts. So this raises the question, should I stop here or should I go further?
We can continue until 12:10. So the 12 cutoff isn't like a hard cutoff. So we can people can ask more questions, or if you want to continue, it's up to you.
So maybe I'll just jump I'll go through it very quickly.
Mm-hmm.
So in quantum theories, there's a potential problem when they are dealing with theories that break parity symmetry. Parity symmetry is symmetry under mirror reflection, which left-handedness and right-handedness. And the standard model is parity violating. The weak interactions are not left-right symmetric. So any string theory that's going to be realistic has to be parity violating. And the theories we knew back at this era were type 1, 2A, and 2B. And the 2A theory is parity conserving, and the type 1 and type 2B are parity violating. So therefore, only one of them might be realistic. But we didn't understand at that time how one could do anything realistic with type 2B. Now, when you have a parity violating theory, there is a potential problem that quantum corrections at the one loop level lead to inconsistencies that you get what are called quantum mechanical anomalies. And these are terms that make the theory inconsistent. This only happens for parity violating theories. So the question arose whether the type 1 and type 2B theories are consistent quantum theories when you study the question of anomalies. And the type 2B theory was the methodology for studying the various anomalies was developed by Alvarez, Gomez, and Witten in 1983. And in that paper, they showed that the type 2B theory is consistent, that all the local gravitational anomalies cancel. And I knew that was going to happen, but anyway, they proved it. And in 1983, we didn't see how to get anything realistic out of type 2B theory. 13 years later, Vafa introduced a non-perturbative approach that he called F theory. So the type 2B could give something realistic. So this result is important in that regard. Anyway, Michael and I decided to focus on the type 1 superstring. Since there we had a gauge group, which, as I told you before, could be orthogonal or symplectic. And classically, this theory is a parity violating theory defined for any orthogonal or symplectic gauge group. So what we needed to do was to compute the one-loop anomalies in this theory. And to do this, we had to look at two diagrams, one of which is topologically a cylinder, like I discussed earlier, and the other is a Möbius strip. And each of these contributes to the one-loop anomalies in this theory. And it turns out that that these two contributions cancel, but only for one particular group. So that out of the infinite number of orthogonal and symplectic groups, only the orthogonal group, SO32, leads to cancellation of the anomalies. Any other choice gives an inconsistent theory. So the type 1 theory actually is a unique theory, not an infinite family of theories. And we were able to develop a low-energy effective field theory analysis where we could analyze gravitational and mixed anomalies, which goes beyond what we had done initially with the string theory diagrams. And when one does that more carefully, one realizes that a more precise description of the Lie group is it's actually spin 32 mod Z2. It has the same Lie algebra as SO32, but it's a different group. So, to our surprise, when we studied this low-energy effective theory, we discovered that the anomalies could also cancel for a second group called E8 times E8. That the low-energy effective theory, we didn't have a string theory, but we could discuss the low-energy effective description of this non-existent theory and show that the anomalies would cancel for E8 times E8. And both the SO32 or spin 32 mod Z2 and E8 times E8 have a couple of things in common. Both of them have 496 dimensions, and both of them have rank 16. And they are associated to the two even self-dual lattices that exist in 16 dimensions. All these facts are deep, and we did not know of a string theory with a gauge group E8 times E8, and we set out to try to construct one, but we were beaten to it by Gross, Harvey, Martinek, and Rome. They constructed a theory called the heterotic string, and they were able to construct the heterotic string for E8 times E8, and it's also for SO32. I think Michael and I would have found it eventually, but they beat us to it. So let me just jump ahead to my conclusion. So the history of string theory is one of unification of particles and forces, of theorists and relativists, of math and physics. It's an exciting journey that's still going strong. Witten has described string theory as the physics of the 21st century that happened to be discovered in the 20th century. Much has happened since then. So an obvious question is, where is the experimental evidence? And that's a good question. We had hoped at one time that supersymmetry particles would be found, but so far that doesn't happen. Recently, there's been something called the dark dimension proposal, which is my current interest, and that suggests some possible experimental signatures that might be accessible. And such a discovery, if it happens, to be honest, I think the odds are against it. But if it happens, it would be revolutionary. So I'll stop there. Any questions? Sorry.
I'm kind of wondering. Yeah, we have a little bit more time. I'm just kind of wondering, to wrap up, like, I have two questions, one of which is kind of like, I think a lot of people have, I don't know how to put it, like scientific dreams. And I always kind of like wondered, like, do you feel like in terms of string theory, like, at its current state that it's something you're happy with, or is there like a dream that you wanted to see that, you haven't gotten to see yet?
Yeah. Well, if the dark dimension proposal works, that would be, as I said, it would be fantastic, because one of the frustrating things is that we have not made a single successful experimental prediction that goes beyond what one understands from general relativity and the standard model. We feel strongly that this is the correct way to unify the two of them in a consistent manner, but it's just mathematics until one has experimental evidence. So this dark dimension idea suggests that one of the extra dimensions could be very large, a few microns. So a micron is a millionth of a meter. It's a big, something you don't need a strong microscope to see. It could be several microns. That's enormous. And the immediate reaction is, that's already known not to be true. We don't see anything in our microscopes. But what it means to be a dark dimension is that only gravity propagates in that dimension. So to visualize, suppose space-time is 5-dimensional. So we think of a slab with two 4-dimensional faces. And we live on one of those two faces. And this 5th dimension is the bulk of the slab. And if there is such a slab of a few microns in size, the only way to discover it is by doing something that's sensitive to gravity. And so what people are going to do is to explore Newton's law, where the force goes like 1 over r squared at very short distances. And when you get down to the micron scale, that 1 over r squared should transition to 1 over r cubed, if there is such a dark dimension. And that, I'm not saying that will happen, but I'm saying there's a chance that will happen. And that would be really exciting.
Are there any experiments ongoing or planned to be going for the dark dimension proposal?
Yeah, I'm not fully conversant of everything that's going on towards this end, but I know that there are several groups that are trying to set up experiments to probe this. The best current experiment is sensitive down to 30 microns, which is already great. The group at the University of Washington who did that work a decade or so ago were awarded a breakthrough prize for that, because we felt it was really important. Another order of magnitude is what we really need here to hope to see something. So 30 microns is great, but it might be closer to between 1 and 10. Well, probably closer to 1 than to 10, but I don't know. And I don't know that it exists at all. But it's a suggestion, which is in its latest version of the suggestion due to Vafa and collaborators at Harvard. Their first paper on the subject, it just came out 2 years ago. I think it is really exciting, because it's the first suggestion I've seen for an experimental test of some of these ideas. So unless anyone wants to say something, I guess we're over.
Sorry. So this dark dimension, could it be identified with gravitational wave interferometry, or is it a high energy physics?
Yeah. So okay. So I was describing laboratory experiments, small science, not major accelerators, where one would probe gravity at very short distances. So it's an interesting question whether gravitational wave experiments could sense this. So one idea that some people have talked about, and I don't know if it's sensible or not, is that maybe, so this may be nonsense. I haven't thought about it enough to be sure. That maybe that gravity waves, which can go through this fifth dimension rather than just on the surface of the slab I described, might find shortcuts over long distances compared to light, which has to stay on the surface of the slab. So if the slab is sufficiently curved, you could imagine that the gravitational wave, after traveling a very long distance, might arrive a little bit before the light. And if you could observe such a time delay in the arrival of the light after the gravitational wave, that could conceivably be evidence for this kind of thing. But I don't know if that's a sensible suggestion or not. I'm not sure.
This is very interesting. Is there any relationship between like ADS, CFT, and dark dimension, like the kind of like the 5-dimensional one?
Right. The ADS-CFT thing is beautiful theoretical physics. It shows how certain unrealistic space-time geometries the gravity in certain unrealistic geometries are equivalent to conventional quantum field theories, and that's which are non-gravitational. And that's amazing, but there's nothing like that for any potentially realistic geometry, as far as I know. So while that's great theoretical physics, and it even has spin-offs in other areas of physics, so it's not just pure mathematics, it's useful for other things. But I don't see how it's going to fit into anything related to a realistic theory of quantum gravity.
I'm kind of coming from mathematics background, so I don't know, but aren't physicists considering some sort of conformal dual to like de Sitter space also, or is that
yes, there's work. Very good. That's a good question. There is work by Strominger and collaborators a number of years ago on DS CFT as opposed to ADS CFT. That work is much less developed and much harder to deal with. You don't have there's no supersymmetry when you're dealing with DS rather than ADS. And supersymmetry is a major tool for keeping your calculations under control. So there's a middle ground between ADS and DS, and that's flat space. And there's a current program called celestial holography, where they're looking for an analog of this, where asymptotically flat space-time is dual to some sort of quantum, two-dimensional quantum theory on this celestial sphere. And that's a subject I got interested in a few years ago and studied for a while. And there's a group at Harvard led by Andrew Strominger that's pursuing that. So it's conceivable that program might work out and give something useful.
Thank you. If there's anyone else asking questions, if not, I'll ask another one. Yep.
Sorry.
Please go.
Dr. Schwarz, I just have a question with regards to so in the Green-Schwarz mechanism, in which you cancel the anomalies in some of these gauge symmetries, you have a classical action given by the Chern-Simons term. I was just wondering if you could speak to any presence of topological invariance in the various descriptions of superstring symmetry that you worked on. specifically with regards to, I noticed the notion of the winding number in the bosonic string theory corresponding to the boson and fermion operators in that theory.
There you've referred to several different things which are each of interest, but they're not very much connected to one another.
Sure, maybe just the first part with regards to the Chern-Simons classical form and the Green-Schwarz mechanism.
So what we did in our physics letters paper is to look at the low energy effective action of the theory in conventional quantum field theory language. And as you correctly said, there's some Chern-Simons business which leads to an anomaly term. And so we had to introduce a new term into the low energy effective action involving a particular kind of field that is known to be present in the string theories. And then there's a long story involving differential geometry and using all the techniques developed by Alvarez, Gomez, and Whitney for constructing an appropriate counter term put into the effective action to cancel the anomaly. So that's all kind of technical stuff, which is important, but in the talk I was more just trying to emphasize the results rather than the technicalities. I'm sorry if I'm not sufficiently responsive. I don't know what else to say.
Perhaps it's my fault for veering too far into the material itself, but I'm interested for the relevance to my own talk.
What are you talking
about? Just mostly topological invariance in quantum computing with regards to the Berry phase as a fiber bundle holonomic quantity.
Okay, good.
So yeah, there's some overlap with regards to the mathematical description.
Right.
Thank you very much, Dr. Schwarz. It's an honor to speak with you.
Thank you.
Following up on that technical question, do you have like an estimate, right? Like you talked about Dr. mentioned industrial. But
Sorry,
like in terms of,
I didn't hear somehow the sound broke up as you were speaking. Can you repeat?
Oh, okay. Sorry, I just have a very broad question following up, right? Because like you brought up these like proposals people have for getting at like experimental, right? So like do you have like a estimate of like how long it for like actually?
Yeah. You're asking how long it will take to do the experiments to test the dark dimension proposal?
Well, not this specific proposal, just in general, right?
Yeah. Well, I don't know of any other proposals to test these ideas. Because most of the stuff is many, many orders of magnitude out of reach. Other than supersymmetry, there's nothing we're suggesting for accelerators. And even there, we don't have any great confidence about it, because the supersymmetry scale might be much, much higher.
Right.
But that's an open question. On the dark dimension proposal, I think that extra order of magnitude in the Newton's force law is likely to be achieved in 5 to 10 years. I think it's not. These are things that can do in small laboratories. It's not big science. And I think there are some clever people who have interesting ideas. One idea in the literature is to make a microscopic system in which where you have two tiny objects in a gravitational orbit around one another. at micron scale. They're like, these are not atoms, but tiny objects, multiple atoms, tiny objects in a, fantastic technology to do this, but there are clever people that I guess think they can. So they would have two tiny objects in orbit, in an elliptical orbit. And when you have 1 over r squared force, at least in classical Newtonian theory, the orbit does not precess. But of course, one of the big tests of general relativity was the orbit precession of Mercury. But the other way to get a precession of an ellipse is to have a deviation from 1 over r squared. So if they can make these tiny orbits of objects and look for a precession of the axis over, that would could be an indication of a deviation from 1 over r squared. There are other ideas too. That's just one approach.
Oh, we're out of time for any further questions. Professor Schwarz, thank you very much for coming and thank you for your time.
My pleasure.